Okay, now we quickly analyze, or at least more quickly analyze a situation where we're given VF, delta t, and A. We begin by just writing down average velocity, average acceleration, straight line graph, and the definition of delta. Okay, these things indicate the triangles that we're going to write. And if we reason out again from the definition of average velocity, we see that that definition leads us to a relationship among the three quantities delta S, delta T, and V bar. Our definition of average acceleration, again, starting with definitions, gives us a relationship among delta T, A bar, and delta V. Our straight line graph tells us how V naught, VF, and delta T are related. And again, we need to think that through. Every time we do one of these problems, we need to think all that through until we really understand it. Okay, and our definition of delta just allows us to relate V naught, VF, and delta V. So, if we know VF, delta T, and A, how do we map things out? Well, before we map anything out, let's just list our variables. Okay, our variables are V naught, VF. It doesn't matter in what order you list these. Delta S, A, delta T. And to be consistent, I'm going to list V bar and delta V in a different color to indicate that they're ancillary quantities that we need to reason things out. But we have our five basic kinematic quantities here listed in blue. Okay, so what is our conclusion? Well, or at least we've got to start before we have a conclusion. What do we get? Can we put VF and delta T together to get anything? Well, the answer is no. Delta T could go together with an average velocity to get delta S, or with a change in velocity to get A, but VF and delta T aren't directly related by any of these relationships. Okay, what about VF and A? Now, at this point, hopefully, we might be beginning to get a feel for things, but we're not going to be able to figure out any direct relationship between VF and A. Again, and then we check the triangles to see if VF and A appear in any of them. They don't. Okay, so we're left with delta T and A. If this is going to work, it's got to work. We're going to have to get something from delta T and A. Well, now, you can look at the triangles, and that's fine. But hopefully you then get to the point where you know that, well, acceleration is the rate of change of velocity with respect to clock time, so we've got a change in clock time in our denominator. So we're going to be able to get a change in velocity. And of course, you might understand that relationship in any of a number of ways and be able to invoke it. But of course, there it is in a triangle also. So we know that one way or another, delta T and A are going to give us delta V. And hopefully we have some insight into how that's done and how that works out. Okay, so now we've got what? We started with VF and delta T and A, and we've calculated, or we've indicated that we're going to be able to find, we know that we're going to be able to find delta V. And hopefully we're getting some insight into how that would be done. But we can always go back to our definition and reason it out. If we don't remember, if nothing really occurs to us. Okay, well, then what? Okay, well, now we know delta V and we know VF. Okay, so we can put delta V and VF together in this sneaked in triangle here. We don't really need the triangle. We know the change in velocity and we know what the velocity ends up. Well, the initial velocity is going to have to be what we ended up with minus whatever the change was. We should pretty well understand that. Nevertheless, we know that we can put delta V together with VF to get V naught. If we just look at the triangle, we see that that's going to work out, and maybe we think about it later. That's fine. Okay. Then what? Let's see. Well, we've now got V naught. And if we got V naught, we know that we can put V naught and VF together to get delta V. And I wrote down delta T, and of course I know better than that. And I hope you do too. Hope you recognize that. But let me write what we get from the straight line graph. V naught and VF are going to give us what? Well, the straight line graph tells us we average the initial and final velocities, we get the average velocity. Okay, so now we can say that V naught and VF give us V bar, and now we know V bar, and the only thing left is delta S. Well, now we know delta S and V bar, which go together in this triangle. They would give us delta T, but we don't need that. We already know delta T. Okay, that was one of our given quantities. So what else is delta S related to? Delta S and delta T related to V bar. Well, it's delta S that we're trying to find. So knowing delta T and V bar, we can get delta S. Now, what are the specific relationships among these things? Well, delta T and A come from the definition of average acceleration. Implies through the definition of average rate that acceleration is delta V over delta T. Knowing delta T and A, we multiply delta T on both sides, we're going to get delta V. Okay, delta V and VF, well, meaning of delta says that delta V equals VF minus V naught. If we know delta V and V naught, then we can solve for VF. Very easy solution. Okay? Sorry, if we know delta V and VF, we can solve for V naught. Did I say that? Whether I did or not, that's what we do. We're going to find V naught. Okay, V naught and VF give us V bar. How do V naught and VF give us V bar? Straight line graph. Of course, that's a straight line V versus T graph. I'm abbreviating, but that tells us that V bar equals VF plus V naught over 2. If we know V naught and VF, then we easily find V bar. We just average initial and final velocities. And finally, how do delta T and V bar relate to delta S? Well, that's a definition of average velocity. Implies that V bar equals delta S over delta T. So delta T and V bar, multiply both sides by delta T, we're going to get delta S. Now let's assume we have something that we know ends up at a velocity of 30 meters per second after traveling for 4 seconds, accelerating at 5 meters per second. What can we determine from these three quantities? Well, we just follow the scheme that we've gotten here just by looking at triangles and thinking a little bit about what the relationships would be. We're going to follow the order of these. Our acceleration being delta V over delta T implies that from delta T and A we can get delta V. Just multiply both sides by delta T, we get delta V equals A delta t, and that makes perfect sense. We multiply 5 meters per second, and I wrote that carelessly. The acceleration should be 5 meters per second squared. Okay, so we have 5 meters per second squared multiplied by 4 seconds. This means 5 meters per second every second multiplied by 4 seconds is going to give us 20 meters per second. So we have our acceleration. Then, the meaning of delta, okay, well, delta V is VF minus V naught. So, what? V naught is going to be VF minus delta V. Now, that's a very intuitive idea, and we want to make sure we understand that. It's just the change in velocity is the change from V naught to VF, so if we know VF, we subtract the change and we get V naught. We want to tell ourselves that. We want to think about that. So, I think I'm missing a step here. Hang on. Couldn't imagine what I'd done wrong. It turned out to be nothing. Something just hit me wrong. Okay, VF minus delta V. We know VF to be 30 meters per second. And delta V to be 20 meters per second. So that V naught is that difference, which is 10 meters per second. Okay, then our straight line graph tells us that average velocity is the average of the initial and final velocities. So we can get average velocity which means we're going to add our final velocity 30 meters per second and our initial velocity 10 meters per second, divide by 2, and we get 20 meters per second. Turns out our average velocity is equal to our change in velocity in this case. That's not something that's generally going to happen, but it happened here, and it certainly can happen. Okay, now we hardly need an equation to average 30 meters per second and 10 meters per second. So it wouldn't be absolutely necessary to write this as an equation because the result is pretty obvious from what we know. But still a good practice to go ahead and write it out so we're sure that we know how to do that. And then finally, our definition of average velocity says V bar is delta S over delta T. And I'm going to have to do that one over here. So and what we're trying to find is delta S, the only thing we don't already know. So delta S is V bar delta T, which is pretty obvious. You multiply how fast by how long, you get how far. But we always want to, until we really master this, think back to all our definitions, okay? Delta S is V bar delta T. V bar is our 20 meters per second. Times our 4 seconds, and that gives us 80 meters for our final result. Once again, thinking through the structure of the situation, reasoning it out, thinking about the meanings, applying the numbers, gives us a much deeper understanding than just plugging quantities into some equations that came down on stone tablets. We will understand what's behind the equations. We'll understand how to think about the motion. We'll understand how to visualize the motion. We'll have a much deeper understanding of the meanings of everything as a foundation for later work.